There's, I'll show those ungrateful streamers. No, wait, what? Okay. Surface integrals by a,
Wizard?
I was going to say amateur. I don't know how to spell that. Is that right? Oh, there's a new movie out with Rami. What's the guy that did Queen? Rami Malek.
Yeah.
It's called The Amateur, where his wife dies from these. He works for as a cryptographer for the CIA, and then he goes on a revenge mission.
Nice.
He digs all kinds of graves. Speaking of which, by an amateur mathematician, because clearly I am not a professional mathematician, because academia has got rid of me. So I'm going to reinvent myself as an amateur mathematician. I don't know if I spelled that right. I can't do English, but I can do surface integrals of vector fields.
Rami Malek.
Yeah. So let's go through this. I don't know why we had to title that. Can you see the green pretty good on there? Does it work? That's the title. Now I'm erasing it. Easy come, easy go. All right, so what we're going to do is we're going to have a surface. Welcome back and all that kind of jazz. I'm not even going to look at it. Oh, there it is. There it is. So what we're doing is we're going to have a region D, which is a subset of R2. And then normally the Stewart calculus et al. Use U and V, but when they parameterize a single one, they use S. So I'm going to use S and T because that's what I use in linear algebra. So we're going to have, oh, it doesn't really matter. This is going to be T, and this is going to be parameter. Let's do it the other way around so I don't hurt my brain. S and T. So we're going to have a point S naught, T naught. And then what that does is it vertically goes up to here, and it picks as a point. If I'm going to use the simplicity for now, but it can be a general surface. But let's use, they're going to use G of, actually let's do it this way. The first thing we have to do with this surface S is describe a region D that is going to be defined under. We're going to extend it a little bit. There, now it's underneath it. And then what we need is we're going to create this parameterized vector R of S and T, or U and V, or theta and phi, or X and Y, depending on whether it's a surface. I like to do it this way because then that gives you a systematic method, and then unlike the Stewart calculus book where they do the special case where the surface, because the surface can be, if it fails the vertical line test again in this direction or any of the directions, what's going to happen is, or you can do it, oh, where were you going? You could come out here, and then if I came forwards through it, in any one of the directions I fail this in the extension of the vertical line test. So what I would normally do if I was going to orientate this surface and do the surface integral, I would use symmetry and I'd use half of it, so the semicircle, because then I can use the positive square root of rho minus x squared minus y squared, which would be g of xy. And then could use this parameterization. We'll get to that in a second. But what we're trying to do is parameterize surfaces. There's a special case when it is the graph of a function of two variables, but I'm going to use this radial vector, and then we'll always do this. No matter whether we use the surface, when we get a nice surface, or we use a plane, or we use spheres, or we use circular cylinders, etc. Regardless of this, they're going to use symmetry to chop it off in half usually to compute this to make it a surface integral, or you can use spherical coordinates and just use theta and phi and define these guys on a rectangular region, and then we can do the whole surface all at once. Regardless of how we do that, I don't like the special cases. I want one all ambient method of actually doing this. Let me get Twitch up too because I didn't prepare myself. We're streaming, go. Where is this? Twitch. Stream. No, I haven't marked your papers yet. They said they had to be due on or at the end of day, April 27th. Today's the 26th, so I guess I'm marking them tonight, and I'll submit your grades later today. Womp womp. Or are they going to do fire me? Bah, bah, too late. So when I do this, we're going to have a region D. There's a lot of moving parts. I have a region D, which is going to be the domain. And then what I want to do is create a function, and then we have a point in space, x, y, z. And so what we're going to do is we're going to parameterize it. Oh, I tried to be a jerk. I don't know why we're using orange. Orange and blue. Where's the baby blue? Then we can go Oilers. Goilers. Did they win? I don't even know. I don't have cable. I can't afford cable. What the fuck is going on? So when we do this, I want R to be, so what I'm saying is regardless of which arbitrary two parameters you pick, always do this, even if it is the graph of a function of two variables in Z or in Y or in X. You can surface this, because if we do the left and right halves of this, that decomposition or charts and atlases of the sphere, or you can do the bottom and the top, or you can do the front half and the back half. Any one of those is going to phrase them as functions of two variables. So what we're going to do with this is, I don't like the Stewart calculus one, so I'm going to start doing it the way that I want. It's a vector, which is a 3x1 vector in 3 dimensions, x, y, z, or z. But now we need to parameterize these as functions of s and t. So technically speaking, each of these x, y, z are going from the domain D into R, which creates a value at each point, this value, which is a function of s and t. So we're raising it up. As you trace out in the domain of s and t, this vector is going to trace out all the points of the surface, and then you can trace out and radially give yourself the surface S. Eventually what we're going to do is vector fields, and so we want an orientable surface, which is smooth and orientable, and so we'll get to that in a second, which means you can just continuously vary the normal vector to that. From the people whose exams I still haven't finished marking yet, you should know that the normal vector is going to be the cross product of two vectors. The ones that we're going to use from that are these guys, the partial derivatives of this, because it's the tangent plane. So first of all, let's talk about, so we have this surface S, and then how we describe this surface S now is with this radial vector R of s and t. Let's just stick to two parameters. Even if it is the graph of a function, which this one happens to be, what you do is you let, they always say in Stewart calculus, let x equal x and y equal y and g equal a function of x and y. But what I'm going to do is show you this. Just make them the x of the first variable, y the second variable, and then z can be the function of x and y, which will be s and t. So then you can describe this, if it is a surface, you're just going to get st and then g of st. And then this will give you always a systematic way of parameterizing the surface, even if it is the graph of a function of two variables. Or in general, you're going to have a more complicated one where it's x of s and t, y of s and t, g of s and t, or z of s and t. But this would be if it's actually the surface of the graph of two functions. In general, you're going to have x of st, y of st, z of st. So that's the special case of this more general scenario. And then in common, the common parameters are you going to use are s and t, x and y, which is the foolish one, or theta and phi, etc., etc. This will be what you know as spherical coordinates. And the book that you probably read is the Stewart calculus one, which is a racket at this stage. And so they're going to use u and v in there. So this is the parameterization of the surface. Now we're going to do linear algebra to do calculus. So don't be afraid of pictures. Once I have this surface S, I want a small change in the surface area because I want this differential ds, they're going to call it. Notice that this ds has no bar on it. It's not the vector yet. We're not doing the vector calculus yet. what we're going to do is the surface integral of a scalar function f of x, y, z, which will be w, which we can't draw. But if we're going to do this surface integral, what we want is what's the meaning of this surface integral over the surface S of this function f of x, y, z ds. We want to know what this is equal to and how do we compute it. And that's the symbol we're doing. So how do we do this? This is called a pullback in the fancy scenarios. We take the radial vector and we pull it back to the surface. We pull the function defined at every point in on R3, and we pull it back to the surface doing composition. All right, this tells me what we're going to do is, first of all, I need this ds, which is a small differential, or it's a small amount of the surface area of S. So I have this surface, and then what I want to do is at every point on there, I want a small amount of the surface area of the actual, so we'll draw it curvy, of the actual surface. And what we're going to do with that is, instead of that, we can't do that, it's approximated by, let's do it this way. This is going to be our S and our T, and I'll tell you what those are in a second. So we're going to create a tangent plane and a rectangle or a parallelogram. So what this means is at every point, instead of doing a little piece of the actual surface area of this, ds is approximately equal to dt, where t is the tangent plane or this parallelogram. And what is that going to be? How do you get this and how do we know this? Well, what we know is that the partial derivatives, the rate of change of this function now of this vector of two variables is going to be the rate of change in the t direction is going to be perpendicular or tangent to the surface in this direction. And the partial derivative with respect to s will be tangent in this direction. So how could I find the area of this parallelogram? Which is approximately, so this is ds is approximately equal to the area, and then we're going to also scale this guy. How much do we want in this region U that we're over for this point? We're going to have a small region, and that's going to be in this direction ds and dt. So this small rectangle is going to lift up into here, and then what we're going to have is we want to scalar multiply this vector by ds, a small amount in the change in s, and we want to scalar multiply this guy by a small amount dt. Now, what is the area of that parallelogram determined by ds times rs and dt rt? Also, I didn't explain this, so for completeness, let's, I moved the table. I'm not going to get my ass this time, table.
Regular viewers of the channel will understand that.
Regular viewers, yeah, it's not, the corner got me one of these days, but I finally cleaned up a little bit.
One of those days,
One of the days, I said. It's like the first time it was an accident. The sixth time, I think he likes it. Shut up. So our s is the partial derivatives. So what that's going to be is the partial with respect to x, or of s of x, the partial with respect to s of y, and the partial with respect to s of z. That's going to give us that vector. I already went back to, you can see, is Pavlovian. I tried to write it vertically, but for simplicity, because we write right to left, and Stuart Calculus has brainwashed me because I got learnt by this. I got learnt by Stuart Calculus too. This is going to be dt of x, and then dt. Put that in the book. I got learnt by this. Dt of z. I never do my homework or the things I'm supposed to, but I'm really good at doing multivariable calculus, so maybe I should have a job. Plato says one of the penalties of not involving yourself in politics is you get governed by your inferiors. So these are the partial derivatives, and these guys will be tangent to the surface, and this is called the tangent plane. Now that small area ds is actually equal to the area of the parallelogram, where I've scalar multiplied it. How far out does this vector go? Well, I can just create this guy, but then I'm going to scalar multiply it by the little bit of dt and ds respectively, so that we have exactly these two vectors scalar multiplied in linear algebra. This is just a number and this is just a number, and these are my partial derivative vectors, which are both tangent to that surface called the tangent plane, to the two-dimensional manifold embedded in R3, which is the surface of a graph of a function of two variables. That's why I call it G, because we need x, which is of three variables. There's a lot of moving parts here. I said some words just now. Words. Now, what is the area of this? I made you do the triangle on your midterm or on your final exam, but we won't do that. I need the area of the parallelogram, which is one of the defining. How could I find a normal vector to this surface? Which we're going to also do in a second. I'll redraw the picture. But the magnitude of this normal vector, which is RS cross RT, the magnitude of that is exactly equal to the area of this parallelogram. So the area of the parallelogram determined by this is going to be the magnitude of RS cross RT. Oh, sorry. Twice you missed, table. Twice you missed me, bitch. All right. What I want now is ds. I need the magnitude of this vector cross this vector times RS cross, oh, there it is again, times RT. These are scalars, and so the cross product rule says what I always say, bring the junk to the front. So I can write this as the magnitude of ds times dt, which are just two numbers, times the magnitude of rs cross rt. This is a number. They're both positive numbers, so we can take those outside in absolute value, but I'll suppress the absolute value. This ds dt we usually call dA. I'm going to get in a second the area of that small rectangle, which is this times this. And then this is times the magnitude of rs cross rt. I know, all of a sudden it looks like, just stop talking about other things. We got Math 120 in your Math 120 class. Don't learn them how to do actual further mathematics. We just want to take their money. This is exactly what now? That's approximately the area of this guy. So that's where you get this from. I'm getting two vectors tangent to my surface, which is not the exact area. The real area of the curve is below it, right? It goes this way and it's arced a little bit, but it's tangent to that, so it's approximately equal to that. And then we'll take a limit and flesh that out the same way as you would do Riemann sums. I'll wave a hand at it. I just did it again. So this guy, therefore, stop saying so. Shut up, Lorenzo. What? He didn't say anything. Lorenzo, your sideburns are too long. So now we have that approximate ds, or the approximate small area of the surface is this linear algebra expression, which we would call this guy, and you can move it. This is a number and this is a number, so by the commutativity of the real numbers, we can do this as the magnitude of rs cross rt times dA. Now we have this function which is going from R3 into R, which is defined at all the points. So we want to pull it back to the surface. And so what we're going to do is compose it with our vector R. And so this is what they call in the book, they'll call it f of R of st. or UV is what he calls it. So we're going to pull it back to the surface, the function. Therefore, we want to know what the surface integral of this function, of this scalar function xyz of ds is. This is computed as a double integral over the region D of f of r of st times, whoa, we ran out of room. Let's do it over here. Let's try it again. The surface integral of s of the scalar xyz of ds is going to be equal to the double integral d, this is how we're going to compute it, of f of r of st times the magnitude of rs cross rt dA, or ds dt if you want. If the region is fairly well behaved, I can use Fubini, Italians, dA. This is how we compute surface integrals of scalar functions. That was a lot of stuff, but you notice that we used linear algebra was the main move there to approximate the surface area. And then you take the limit of those guys, and then it fleshes out to exactly this, the same as you would in the one-dimensional calculus when I break this up into rectangles, and then we take the limits of those and you get exactly the area under this guy. That's the extension of the double integrals. Now we want the surface integral of vector fields, because we want to do calculus and flux of how much energy is in. Gauss's theorem says that the amount of energy in the sun is the same amount as the flux coming off the surface at any given moment. So let's do that again. Oh. Now I have a vector field in 3 dimensions, which I definitely can't draw because it's going to be in 3 dimensions. So let's draw this properly for a second. I'll draw it horizontally again in a second, but this is, whoa, this is going to be, what do they use in Stewart? They use P of x, y, z, Q of x, y, z, and R of x, y, z. Vincent Bouchard used F and G and H, but then that hurts my brain. So sorry, Isha, I'm going back to P, Q, R. What that does is I'm in 3 dimensions to 3 dimensions. So this would be the domain and the codomain. For every vector xyz or point xyz in R3, I'm going to create a vector defined some way. If it's gravity, gravity sucks, dark energy blows. So it's going to point inwards at every point to the center mass, etc., etc. We're not going to get into it, but it's going to create another vector, which will be P, Q, R for simplicity at every point. So this is what a vector field is doing. For every point or vector in R3, it's defining a new vector, which will be pointed radially inwards if you're doing 2-point masses and we're talking about gravity. You have to normalize it, but that's okay. It doesn't matter. It's divided by the norm to the 3 over 2. The square root and then cubed, the inverse cube law. Newton, it's inverse squared, but then there's a 3 in there. Science. All right, so now we have a vector field. What this vector field is going to do now, what we want to know is, we want to know how to take the surface integral of f dot ds. And so what is this? What we need first of all is an orientable surface. And so what that means is if we have a smooth orientable surface, this is going to create at every point. What that means is as you vary the normal vector, you can vary it continuously. The classic one of an unorientable manifold is the Mobius strip, which is unorientable, or, where is it? I have a Klein bottle in here somewhere. The Klein bottle, which is the projection into 3 dimensions. But the Klein bottle, this if you look at this, the ant ends up upside down, so there's not two sides to that surface, even though it looks like a sheet of paper. If you put one twist in it, there is no sides. There's only one side because the ant can just get on either side of the piece of paper. The Klein bottle is the three-dimensional or the two-dimensional manifold analog of that. And what that is the Klein bottle can hold fluid, but it has no inside or outside. Weird. That's unorientable. So we want orientable surface. If you do this, and for most parts, what we're going to do, even if even if the surface is fairly complicated, we want to use some kind of symmetry or be clever and create it as a graph of a function of the first kind, where I'm just going to call x equal s and y equal t, and then we'll create g of st as the z coordinate. But you can put this in either one of the spots where you could do this if it was on its side, or whether it's front facing, whether it's pointing this way out at us or on the side or up and down. But the way we classically view this is the up and down one. So when I teach a first class, or we just do an arbitrary rant of a madman, we're going to use the classic one that I'm using. Now, if you look at this, we're going to redraw this. And at every point there, I had a natural way of how could I create a normal vector to this guy. And I want the unit normal vector. It turns out that this is equal to, the way we define this flux is that this is the surface integral of, we look at this as, the way they derive this is if you have, say, a fish net in the water, how much fluid is flowing through the fish net at any given unit of time, etc. And so what this happens to turn out being is this guy, the unit normal vector. When we flush the fluid through this, it's going to be the dot product from linear algebra of the unit normal times ds. And so this is how we get rid of, the first time we do this without doing a bunch of physics, the first way you do this, if I'm going to do the surface integral of a vector field, now I have a ds. How do I get rid of that? I get rid of the bar on the ds, or the vector ds, by using the unit normal component of f dot dn. When you look at that, when you do the algebra, it works out, but I want to spare it. I was going to do some examples, possibly, or make one up of some parameterizations. And then what we want to do is, that's the unit normal vector, and then we have this ds. N is the unit normal vector, so if this is rs ds times rs and dt times rt, then the normal vector is going to be, we don't need to scale those anymore. We scale that for the ds, but that's going to be the magnitude, or sorry, it's going to be rs cross rt, and then how do you create a unit normal vector? You divide by its length. So now this is the orientable manifold. We can upwards orientate it, and this will be the unit normal vector. If you use the negative, you can do the downwards or the inwards orientation as well, but usually they want the outwards one, so you can see what flux is coming out of this. Now, what we want to do is put that there, and then now we already know that I derived ds. ds is cleverly rs cross rt times ds dt, or dA. And so what that says is we can put that all together and it cancels out nicely. The flux off of a surface of a vector field over a surface is going to be the surface integral of s of f of r of st dot product with the unit normal vector, which is rs cross rt over the norm of rs cross rt times rs cross rt, the magnitude again, dA. So this cancels, and we get, sorry, that should be the region D. And then we're going to get that this is just equal to the double integral of over the region D of f of r of st, the pullback, dot product with RS cross RT dA. And this is the dot product, so it's just a scalar in S and T now. And that's how we compute surface integrals of vector fields. We use the surface integral of the vector field is the surface integral of the scalar. This is the dot product of the scalar of the unit in the direction of the unit normal vector. The unit normal vector we derive as RS cross RT from that tangent plane, and then we divide it by its length to get the unit normal vector, and then ds was the small amount of the surface area, which was this magnitude times dA. Those cancel out cleverly, and this is what the book is going to produce for you. And so that's surface integrals in and of itself. If we're going to do an example, oh, this chalk. This was a bad idea. Okay. If we have, let's just do the upper hemisphere. So what is that? Now we're going to use, where is that going to go? Theta is going to be between 0 and 2 pi. So if we make theta this horizontal direction, here's 0 and here's 2 pi. And then where's phi going to go from? It's going to go from 0 is up here, and then pi over 2 is halfway from here. This is the phi that we're doing. You could normally go all the way, but we're only going to go halfway. And so that says that if this is the theta, then the rectangle that we're getting, Fubini, is going to be 0 to pi. And so there's the region D that we're using. There's my surface S. And now if you want, let's just create a nice one. F of x, y, z is equal to x0, y. I don't know. Yay, let's see what happens. What is R? R is equal to what? R of theta phi is equal to, do we remember? Let's call it the unit. Should we use rho? Okay, we'll just use rho. So that's the sphere centered at the origin. Let's use the unit one at least. So it's going to be rho cos theta sine phi times, or sorry, comma, rho sine theta. Basically, it's polar coordinates, and then you add sine phi, and then the last coordinate is rho cos phi. There's the parameterization. Do you remember what the magnitude of our, so if you're going to see this now, what I have to do is take the two partials. Can we do it just for poop, shits, and giggles? I can say shits and giggles. Poops and tickles. Poops and tickles. PG, bruh. A PG. What is our theta now? It's the partial derivative with respect to this. So this is going to be equal to negative rho sine theta sine phi rho cos theta sine phi 0, and our phi is going to be equal to rho cos theta cos phi rho sine theta sine phi negative rho sine phi. Then we have to cross product those, right? Is that what I get? Oh crap, well, now we're going to have to, x0, y. That's still going to be sucky. I don't want to do that anymore. I'll leave it to the reader to do the rest, but let's keep going with this. What is this going to be? Now I want to do r theta cross r phi, which is going to be I, J, K time, I should leave myself more room, because that's going to be this guy, right? Yes, this is the first one, negative rho sine theta sine phi. There's a formula, but I just wanted to show you that you can do this if you forget. Don't memorize, rememberize. See what I'm doing? I'm rememberizing it in case I get it. It's rho squared sine phi, right? You'll see in a second. This is going to be rho cos theta sine phi 0, thank Christ. Rho cos theta cos phi, rho sine theta sine phi, and then negative rho sine phi. Close this. I don't need those anymore. I need this guy, but I know what it is, so we'll just get rid of that. Oh, that was the spherical coordinates of the hemisphere that we were doing, the units, not the unit sphere, but the sphere centered at the origin with the radius rho. Now I have to do this cross product, which is going to be I times what? I block off this, so I'm going to get this guy times 0, which is going to be rho, negative rho squared sine squared phi times cos theta. That's a negative, put brackets, minus j times, we'll block off this. It gives me positive times this guy, this, but then that's where I get the negative. So then that's going to give me rho squared is that right? Yeah, because I need the magnitude. Yeah, that's good. So this guy I'm multiplying. So sine squared phi sine theta, and then plus k times, what do I get? I can block off this finally. Oh, crap. K times this junk, which is going to be what? Negative rho squared sine squared theta minus, I said theta, minus rho squared cos squared theta times negative rho squared sine squared theta minus rho squared cos squared theta. Did I lose everybody yet? I almost lost myself. Sine squared phi. That's the last component here. I'm multiplying this minus this. And notice that that gives me what? 1. So this is negative rho squared sine phi. Good. Now I need the magnitude of that. No, you thought we were done? No. Now I need the magnitude of this guy, which is equal to what? The square root of this squared plus this squared plus this squared. But do you see it again? I'm going to get rho to the 4 sine to the 4 phi cos squared theta. Did I do that right? How come I get a factor of 2 now? Did I do something wrong? That's the first one, right? Mm-hmm. And then plus this one, which will be rho to the 4 sine to the 4 phi times sine squared theta plus rho to the 4. How come I got a 2? What did I do wrong? Did I do something wrong? Times sine to the 4 phi. Oh no. Noodles! Get over here. The big black cat. I need to think about what I'm doing. So it's like, stop and get a cat and pretend that you know what you're doing. Hi. You were going to go see all the other guys? Okay, go see them. Go say hi. He's going to try and get you to give him food. Don't listen to him. I didn't do it. I didn't get a 1. Just a second. Do you see it? You're like, no, you're driving. I thought I got a 2. I was trying to calculate it in your head. Don't do that. Write it down. That's why we got algebra. So in the first one, I see that I have this guy, and that's going to be a 1, right? And then I have rho to the 4 calculated by, so that's going to give me a 1 by simplification, and then that's going to give me no, it did. Wait, what? Oh, crap. One of these is wrong, isn't it? There, I just assumed, right? Oh no, that's cos squared. What did I do wrong? I did something wrong, didn't I? I got rho to the 4 out, and then I have... Oh, I can take out the... Oh yeah, no, there it is. There isn't one. I can also take out the sine phi, right? And now I have... What do I have left? No, I do. I have a 2 for some reason. I don't know why I got a root 2. I must have made a calculation error somewhere. Because I have cos squared theta plus sine squared theta plus 1. I don't know. I lost myself. I'm not redoing it. Are we redoing it? Damn it. Oh, I erased my thing now.
X0y, X0y.
Yeah. So, did I do each of the components right? Now I got all fancy smancy pants.
Do you want to look it up, or?
No, I know what it is already. That's why it's tainting it.
Curse of knowledge.
It should be rho squared sine phi, right? So I think I've got a calculation error in there.
This is good for pedagogical reasons.
Yeah, if you think you get the calculation right every time, you don't. So let's recalculate the cross product. This is equal to, let's go slow, I times, what do I get? It's this one blocked out.
You get a rho squared, right?
Negative rho squared, yeah.
And then cos theta sine squared.
And then minus j by cofactor expansion times this one, which will give me positive, but then that's where the negative gives, rho squared, and then I have sine theta, right?
Yeah, and then
Sine squared phi, I said, and then plus k times, I think it might have been this one that I did wrong. So it should be rho squared sine squared theta sine squared phi. That should be a negative. And then a negative here, and that's why I get a minus rho squared. I got the same computation. I don't know what I did wrong. Cos squared theta sine squared phi, which is equal to, as a vector, I have negative rho squared cos theta sine squared phi this one gives me negative rho squared wait, maybe I did that, sine theta sine squared phi, and then the last one is negative rho squared, and then I have sine squared plus cos squared, so that should be negative sine squared phi. It's the same problem. Okay, now I'll do it, son of a bitch.
Don't be shy to refer to your materials, right? That's the pedagogical lesson here.
Oh, that was awfully serendipitous, but it should be, there's polar. Where's the spherical coordinates?
One flip, almost.
Dun, 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 dun. All right, what the fuck? This is exciting. This is thought-provoking live streaming.
Gotta put on that the music like in
Dun, 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 dun,
when you're standing up
dun,
forward.
dun, dun. Yeah.
Eye of the tiger.
That's right, yeah. That's it.
10:45. $41, $42 for the 45. Spherical coordinates.
Whoops. All right, there we go. Now this mic is on. So while Adrian is looking that up, maybe Tim and I will say a few words about not hesitating to refer to your reference material.
Well, once you get past having an ego, you realize that doing math live in front of an audience is a risky business.
Absolutely, and actually, this is what earns you the title of wizard, is knowing where to look.
Exactly.
Yeah.
Intelligence is not knowing everything, it's knowing where to find what you need.
There you go.
I can't remember who said that, but that's a quote from some dead Frenchman or dead Greek or something.
One of them French mathematicians, yeah.
Or the German ones too, but they usually go, spit. But,
Or it could have just been you that said it just now.
I'm not taking credit for that. Because someone will call me out. I'm going to look it up.
Well, that's good. We need the, the only bad publicity is no publicity, right?
Well, this is true. This
There
is
you go.
true.
I must have made a mistake. It's telling me that. Wait a second.
Made a sign
Could have been, or
Well, what they do to get rid of the negative in it is they just do rho phi cross rho theta cleverly, because if you interchange them, you'll get the negative. But they're telling me that I found the flux off of the unit sphere, which just means the rho will go away. Example 16.6.10.
which edition is that? 8 or 9?
The 8, I believe.
8. There you go. 16.
editions, they'd have the bugs worked out of it.
No, those are the features. Is they're introducing more bugs
yes.
into each edition. Now with more bugs.
It's not a bug, it's a feature from software development.
Oh,
Exactly.
here we go. Why did I get it wrong? They used A and they interchanged these two. So I have a row. Did I do that wrong? They're claiming it's this. So they interchange the two. I found it though. So let's change it so we get rid of the negative. I, J, K. I must have done fast my partial derivatives. I must have done wrong backwards. They're saying that this is A cos. Oh no, wait. Yeah, cos phi, cos theta. Maybe I put sine thetas in. I don't know. No, now I'm just making it up. So that's a rho, and then this is rho cos phi, cos theta, negative a rho. I'm copying sine phi, and then the zeros down here. Negative rho sine phi sine theta. I thought that that's exactly what I had. Rho sine phi sine theta.
I think the 0 might have been in the wrong spot just from copying it down wrong.
Well, I just interchanged those two,
Oh, well, there you go. Never mind.
which will get rid of the negatives, is what they're doing.
Is the lesson there to be less negative?
Yes.
Wah,
Womp womp. So then they're saying the magnitude is the square root of row 4 sine 4 phi cos squared theta. Oh, fuck, I'm an idiot. Okay. As soon as I looked, I had it all right, and then there's one mistake in there. Plus row 4. Oh, crap, now I'm going to frickin' get it wrong. It was yeah, okay. You'll see it in a second. I had it right the whole time, I think. I just didn't see the identity. I was trying to go too fast. This is phi, and this is sine squared theta, and then this is rho squared, and then it should be a cos, I believe. So this first one, it gives me the identity, right? So I can take out I think I had the cos, that was my error right there. So I have the row 4 I can take out for sure, right? And then in this first one, I have sine squared plus cos squared, which gives me a 1, which will be, no, fuck. Now I lost the page of the page that I lost that I had it on. 16.11.10. It's funny, now you wonder why, also this is why I like theoretical math, because all of a sudden you go to start computing something, it's like, wow, fuck, I made a mistake, I don't know. Yeah, there. It's there. Fuck's sakes. There's a sine squared phi in here too. I missed it both times, even copying it out. Row 4, sine squared phi cos squared phi. I missed it twice, right? Because it's sine squared theta times sine times phi. Okay, so now I get sine to the 4 phi, right? And I get the 1 here. I'm not writing it out, but there's the 1 that'll disappear in these first two terms, right? Plus, now, do you see it? Sine squared phi cos squared phi. I missed the cos squared, or the sine squared in this component both times I did it. So now I can take this as the square root of rho to the 4 sine squared phi times, I knew there was the sine squared in both of them, and I'm like, how come I'm not getting it? It should be sine squared phi plus cos squared phi. And this goes to 1 now, which will be rho squared times sine phi. Yay. Also, this is a really good lesson onto, I'm allergic to this chalk, but I'm all chalky now. But x0y, right? x0y. That was what now? This guy.
Just one piece that we needed to chop up before putting it in the Tutor.
And then that's why they give you the formula and the spherical coordinates. They say that you could do that, or that's the small differential. But now we want to do the surface integral of the vector field f dot ds, where our surface was 0 is less than or equal to theta is less than or equal to, oh crap, now I'm still not going to do that. You can do that. I've already made enough mistakes today. Maybe we could do it. It's going to be some horrible number. Give me the blue chalk. And this was 0 is less than or equal to phi is less than or equal to pi over 2. Might not be too bad because I don't think we get anything because I just made it x and y. This is going to be equal to the integral over the surface S of f dot n ds I didn't even need it because we're doing a vector field, which is funny. Oh well. That whole calculation was useless anyways, which is going to be the integral over the region D of f of r of theta phi times r theta cross r phi. I didn't need the norm, but it was good to find out. dA. So what is that going to be? We need the cross product, which was, now I'm going to look it up a third time because I'm lazy. Also, I'm lazy as a mathematician. Oh, that was almost perfect. Perfect.
You kind of need to be lazy as a mathematician, right? Then you find the easiest way to do something. But that was a very exciting calculation, actually.
Yeah, it shows you that I used Pythagoras' theorem twice. Green's theorem, parametric surfaces.
In math or science, you can never escape Pythagoras' theorem.
Nope. 23-ish hundred years later, and this theorem still reigns.
I guess the universe is entirely made of right angle triangles.
There we go.
Not tiny little squares, they're triangles. Which are squares cut in half.
It's just glue two of those triangles together. There you go.
And if you flip it around, then it's
How come I can't find it anymore?
There you go.
16
you could just be
points.
making up words, I don't know.
Would you say that maybe the triangles have something to do with these circles that form the quantum loop gravity structure?
Well, those are CW complexes, and there's that guy, and then the triangle, and then the tetrahedron, yeah.
Going up in dimension, right?
Yeah.
There you go.
So you can have a hypercube. Can you have a hypertriangle?
You probably have a hyper anything, right?
Possibly.
Well, it's not called a triangle in 3 dimensions, nor is this, well, yes.
Could be a prism of some sort or a
A
pyramid.
hyperprism?
They're called CW complexes.
A
there we go.
hyperparallelepiped? If we're gonna go.
CW complex is what it is.
Yes, you have this, and then you have this, and you have a triangle, and then you have a pyramid, and then you can go higher than this. So yes, you triangulate everything. That's why they call it triangulation, not squarelation.
Squarelation, did I hear?
Squirrelation? What?
Squirrelation.
That's where you start hoarding your nuts for the winter? Squirrelation?
I hoard my nuts every night.
Well, is that followed by busting them?
Dear God.
Oh, that's the new movie with Ryan Gosling, Project Hail Mary. The
Yeah,
aliens like bump my fist or fist my bump because he wants to do a fist bump.
Not
He's like, that's not the
communicative.
same thing. He's like, I'll do it, but that's not that's not the same thing.
It's a non-commutative.
Yeah. So
Operation.
Rx cross Ry. So R theta cross R phi is equal to crap. I'm winding it down. Math is hard. Rho squared negative because I've done this way. Sine squared phi cos theta. Rho negative rho squared. Sine squared phi sine theta. And here's where I missed it the last time. It's negative rho squared sine. I kept writing it, but it's sine phi cos phi. That's where I made the mistake every time. Let's leave that page open instead of closing it for the third frickin' time. Shame on me. You know what I mean. George Bush.
Bushisms.
No, I
Bring
don't,
back
George.
Bushisms.
No, I don't, George. Tell me. Tell me. Fool me once, shame on you. Fool me twice, shame on me. So this is the cross product. Now I need my vector field. What is f of r of theta phi. What do they mean by that? Well, I have to take my vector field, which was x, which is just going to be now what's x. Now it's blending in there. Let's move it over again. F of r theta phi is going to be equal to, I just said x, and then I'll take a 0 any day. 0. And then x is just what my parameterization. So what is x? Rho cos theta sine phi was my x, and my original r of theta phi was the parameterization of the sphere, x, y, z. So now I called it that, and then I called it y, which will be rho sine theta sine phi. Now we have to dot product those two together. Crap sakes. Crap sakes. I picked, and then you see why I picked an easy vector field for myself, because I knew what was going to happen. I knew it was going to blow up. I didn't think it'd trick me where I wrote this down wrong twice and I had to look it up in the book. But where's the answer books? What are we going to do? The surface integral now is Fubini, but it was the integral from theta, d theta, d phi, so 0 to 2 pi, 0 to pi over 2. You can write brackets in there to clarify this for yourself if you want, because then that one is d theta, d phi. And now it's Fubini, and now what is that? F of r of theta phi dot product this, so I'm going to get, oh crap, negative rho cubed, which is a constant. See, that's where we're going to have to use trigonometric integrals. Sine cubed phi times cos squared theta. That 0,
Wishful thinking that it was going to be that short of an integral.
minus rho cubed times, what do I get? Holy, that's not too bad. That's a phi, right? Yes. Sine squared phi times cos phi, substitution rule, sine theta, d theta, orange bracket, I said, orange bracket, times d phi. So, what is that? A hot mess.
You beat me to it. I was just about to say that.
Which is equal to, so now what we're doing is we're holding phi constant. So we can split this up. This is going to be negative rho cubed sine squared. We can even do this, because it's Fubini and these functions can be separated. We can separate this, so we're going to write this as negative rho cubed on the outside times the integral from 0 to pi over 2 of, in the first one we have sine cubed phi d phi times the integral from 0 to 2 pi of cos squared theta d theta plus the integral from 0 to pi over 2 of sine squared phi cos phi d phi times, I ran out of room, the integral from 0 to 2 pi of sine theta d theta, square bracket. Now you can do that. What do I do with this one? We're going to run out of room, so let's do this one first, just as integral. I'll set it up for you and then you can finish it off. In this one, I have to write this as sine squared theta phi times sine phi d phi. And I see substitution, so I'm going to let W equal cos phi. How did that one turn into that? Again, from Pythagoras' identity, that will be 1 minus cos squared phi. And then the differential I'm looking for, whose differential would that be? So this would be dw is going to be, or negative dw will be sine phi. I could take that negative and use it in here, in this one. And so, that just hurt my brain. So we'll keep that.
That was a good move, though.
D phi, yeah, you can see that we're going to do that. And this one, what are we going to use? This is the danger case. This is the even one. So that takes care of this. You also have to change the bounds. When cos is 0, we get W is 1. And that'll get rid of the negative also. So when W, or that'll go from W equals 1 to W equals 0. And then you can flip it to put it properly, or change back into phi if you want. This integral is going to be cos squared theta is 1/2 1 plus cos 2 theta, and then you use a substitution. W is equal to cos 2 theta, then dw is equal to 2 negative 2 sine 2 theta d theta, and then that'll be negative 1/2 dw is equal to, oh no, wait. Yep. That was too much. That'll do the substitution for that one, for this guy. Change the bounds, and then this one is just a substitution because now I have that. This one I would write W equals sine phi, and so W is equal to cos phi d phi, and then this one is, that's just the integral of sine, which will be negative cos. Put it in your values and suck it up. I always say, I'll crack the eggs for you, you suck up the yolk. I'm done with this stream. I'm going to frickin' sneeze everywhere. My hands are super blue. Go Oilers. Let me make one.
You blue dabba dee dabba da.
Do babba dee. Go Oilers. Can I? Oh wait, we're going to do something really stupid in a second. SMRT. Did it work?
No, but we get the idea.
Go Oilers.
All right, thank you, everyone.
These Oilers. Go Oilers.
There you go.
That's they cheer. That's how they cheer in Tel Aviv.
Yeah.
Not quite.
Goy Oilers. Yes.
Oh. No, that's Australia. Oi! Oi!
All right.
Look.
Goodbye, everybody.
They're trying